So, yeah, I understand that there has been a shift in favor of nuclear energy in the past years in Norway. And also there is a growing interest in understanding the benefits and the risk associated with electronuclear energy. So in my presentation, I will introduce my background, share some experiences in the field of nuclear energy, especially about the EPR, which stands for European Pressurized Reactor. This is the reactor designed it was designed in a collaboration with France and Germany. And I will briefly also present other alternatives like the small modular reactors. So I will focus mainly on the industrial aspect of nuclear projects, including the EPR construction, how to say, including, the construction phases, the challenges faced in the recent EPR construction projects, especially those who led to delays and cost overruns. So I might sound a bit critical during this presentation about EPR, but I'm fully supporting this technology. I just want to show you specific aspects that I think are relevant to be aware of when approaching this type of project. So the goal is not to show you that these projects are not worth the cost, but rather to provide you with a deeper understanding and challenges encountered for your consideration for Norway. So I choose to concentrate on the industrial aspects, as I have noticed on your YouTube channel that it covers already many things, like the background of Norway in the nuclear energy, for example, or the waste management, the regulatory aspect, if I'm not wrong, and also discussions about the interest of nuclear energy in Norway in the energy mix. So before going to the presentation itself, I think I can say that Norway, in my sense, already has a vast amount of technical knowledge required for electronuclear projects. And even though there are specificities related to commercial nuclear energy, Norway has mainly focused on experimental plants. But most of the necessary skills are, in my sense, already present in Norway, and also some necessary institution already exist as well. So yeah, as you introduced me, my name is Lova Andriamasy. I studied in France, and I'm an engineer, and I've worked for over 10 years in the field of nuclear energy, particularly on the EPR project, which has been so far developed in France, Finland, China, and England. So just to present you my experience, my main expertise focuses on the operating of the power plant during accidental or incidental conditions. Here you have the control room of the EPR with the operators and screens provided that provide the necessary information for the plant operation. So as you may know, the EPR is the technology that has been adopted by Finland at the Kyoto site. And each EPR has its specificities, but I work on the reference operating document, which are standard, but then adapted to every EPR project based on the client needs. So on the bottom right of the screen, I don't know if I can put the laser here. Yeah, in the bottom right of the screen, you can see the operating documents used during the incident or accident. These documents exist both in digital and paper versions. The paper versions are used in case of screen loss, and operators switch to conventional synoptic platform with like physical buttons for maneuvers. You can see here on the left side, it's a bit small, but you have the screen, the digital, and then if the screen shut down, the operators can go to the manual. So if you remember Fukushima, and the Fukushima accident, the information were actually lost in the control room, and the operators were confused and didn't have clear enough procedure to manage the issue. So these documents precisely described the actions to be really strictly followed. So we developed all these procedures and images used to manage all the accidents. And for instance, in this image here, you can see what we call the sock because of its shape. It looks like a sock, and it draws the limit of the normal operating zones in terms of pressure and temperature in the core reactor. So the operating point should always be inside, and if it goes outside of this domain, for example here, then we enter an accidental phase, and we have to manage the situation to put the temperature and the pressure of the core reactor inside this domain again. So that's what I do. So so I'm gonna be a bit technical. I hope I'm not gonna lose you during this presentation, but hopefully it's gonna be useful. So these situations, accidental situations, if you remember Fukushima, require really well identified and reliable coordinated action among the team members in the control room, and really the strict adherence to the safety protocols are crucial to avoid unintended action. So the operators must strictly follow the procedure throughout the incident until the plant reaches a safe state. So after Fukushima, these procedures were strengthened and integrated all the improvements necessary to enhance the reliability of the operators' action during the situation. So I worked on this topic at EDF in the engineering office of EDF, which is the Electricity of France. You can see the logo here. And yeah, the EDF is the sole operator of nuclear park in France, and is 100% state-owned. Also, EDF works internationally and is involved in construction, but also sometimes operation of the plants, as is the case, for example, in England and China, where I worked for a few years. So about the EPR, in fact, the EPR, even if it's the latest a more advanced nuclear power plant in the world so far, the basic technology of this type of nuclear power plant has not really changed over the past 30 years. And all improvements have been made to focus mainly on safety rather than the energy production. So the picture here illustrate the nuclear power plants and the safety systems designed to protect the public and environment in case of accident. For example, here the containment system is designed to contain the fission products in case of core meltdown. And as you can see here, there is a double wall reinforced in concrete to really protect from aggression from outside. And it's also, for example, designed to resist the plane crash. So also the safety systems are redundant. Meaning they include multiple independent operating devices, and this increased the likelihood of safety system functioning correctly in case of accident. So this redundancy especially are designed for cooling system to maintain the reactor core at the safe temperature. So additionally to these safety mechanisms, such as emergency systems, there are also here containers that capture the core meltdown in case of accident. So in a nutshell, every improvement today in nuclear power plants are made to enhance the safety of the nuclear power plant. Here we can see that Areva, which is the French developer of the core system, has built around 100 nuclear reactors in 11 countries, which represents almost 30% of the total installed nuclear capacity worldwide. And Areva and EDF are the core French team for the EPR. The diagram here, the graphic on the right, shows the lifespan of nuclear power plants worldwide. And I'd like to emphasize here the substantial amount of data available thanks to the extended operational history of nuclear reactor globally. The total operating hours of a nuclear power plant in the world is estimated around 100 million operating hours, which is very big. And the five, let's say, top countries which has the most nuclear power plants are the United States, France, China, Russia, and Japan, can say. So to get this million hours of operation, the calculation is just to take the average age of the nuclear power plants and multiply by the number of power plant. So by doing this multiplication and addition, we get to this 100 million of operating hours of power plants. So while it is crucial to continue improving the safety of nuclear power plants, even though there is all this knowledge, the new plants in my mind, achieved a very high level of safety. The objective of nuclear safety, which is the priority, the absolute priority actually in the nuclear industry, is to ensure that all operations comply to the highest safety standards while maximizing the benefits of its energy. So there is a central document in the validation process of the construction of a project of a nuclear power plant, and this is called the safety report. So this safety report is a central element in the review of application for a construction, and it's needed for the operation authorizations of a nuclear power plant. So how it works is the nuclear safety authority of the country ensures that nuclear power plants are designed, built, and operated to guarantee a high level of safety. So this safety report must guarantee the safety of people, the safety of environment as well. And that's the job basically of nuclear safety authorities. They have to be comfortable with this report before launching or authorizing the construction of a new power plant. So during construction phases, the authority assessments or control have actually led to many challenges in the project, and it has resulted in many delays and cost overruns, as we will see it a bit later during the presentation. So in France, for example, the safety requirements have been a factor of delays in the construction of the EPR in Flamanville in the north west of France. But it also shows that safety was at the end more important than respecting the deadline or the financial constraint. Next here, so just quickly, so nuclear energy has been my a significant part of my career, but I initially worked in aerospace. So it's not about nuclear, just to show you quickly what I've done also complementary to the nuclear sector. So I began my career in Paris in aerospace, working in on the Ariane 5 launcher of satellite. I was involved in analyzing the failures that led to led to delays and cancellations of the launch of the launcher. So for Ariane 5, the launch here zone, as you can see here, was far from the assembly building. And the problem was that during the transport from this assembly building to the launch zone, technical problems occurred, and sometimes we had to take it back to the assembly building, and 1 day of delay cost around 1 million euros. So we had to analyze all the potential defects and also propose a new platform to avoid this time-consuming back and forth in case of problems. So what we did at the end is to build the assembly building directly in the launch zone to save time. And today for Ariane 6, the launch zone has been modified so that yeah, everything is in the launch zone, and we saved a lot of time, which allowed also the European Union to remain competitive in the in the global space market of launchers. For the past 5 years, I've been working for the World Bank in the energy sector, especially in developing countries, particularly in Africa, where the access rate to electricity is very low. So my work involves advising governments to develop and implement their national programs for modernizing the energy systems and improving the access rate to electricity. So this involves a broad range of activities, for example, in terms of governance, in terms also in facilitating investments in the energy infrastructures. So this includes a really broad number of activities. It covers the production system of electricity, the distribution networks, also the institutional reforms, and the choice of technologies as well, especially renewable energy sources. So the one I would say key aspect of my work was to mobilize the financial instrument to establish public and private partnerships. So let's go back to nuclear power plants. So first of all, there are several reasons that motivated me to present the EPR, the EPR technology for this presentation. First of all, that's the field I master the most. But the EPR is also an international project where the owner and the client belong to different countries. And I imagine that if that this would be the most likely scenario for Norway if Norway decides to have a commercial nuclear power plant in the near future. So also the EPR is a pressurized water reactor as a technology, and this is the predominant technology among the 440 reactors in operation worldwide. So it is therefore the type of reactor that does the most operational feedback. And I think it's important to have it in mind when deciding which technology would be best suited for a new power plant. So the experience with the first EPRs, as you may know, has been quite painful so far due to delays and cost overruns. But it's also a lot of valuable information as it is reality for any new industrial project where the first units usually face challenges. So despite the delays and high cost of the EPR project, 2 years ago, France has launched a massive plan of 50 billion euros to relaunch the nuclear power plant construction in France, which confirms also the ambition for further developing this technology. So the ambition is to build 6, as you can see here, 6 new EPRs in the 10 to 20 years, but the government wants to go further. So today, I would say that after almost 3 decades of political uncertainties, in France, the planets are now aligned to really build a clear path to the development of the nuclear sector in France. So the objectives are, I would say there is 3 main objectives. The first one is to achieve the carbon neutrality by 2050. As you know, nuclear power is a low carbon energy source, and it will play a significant role in the French energy transition. Second point is that it will strengthen the country's energy security. Nuclear power is a reliable energy source that reduces France's dependence on energy import, especially oil, because even though France has 70% of electricity covered by the nuclear power plant, there is still share of the electricity production produced by fossil fuels. And the third point was the job creation and economic activity. So the construction and the operation of nuclear power plants, the new ones, will create thousands of new jobs and economic activities in the nuclear sector, but all the industry around. Here I wanted to show my understanding of the Norway environment in terms of energy. So far my understanding is that currently Norway is reflecting about the trajectory of its energy mix, given the objectives of carbon neutrality, but also the increasing demand of electricity. So on this slide, the graph on the top left shows the electricity interconnections between Norway and the neighbors. On the bottom here, the graph shows that Norway is a net exporter of electricity most of the time. On the top right, the energy consumption graph shows that some activities such as transport, agriculture, or construction are still quite dependent on fossil fuels. And this graph here in the bottom right showed that electricity consumption has raised for the past 30 years, while the energy production has remained relatively stable. So we can understand that as electricity needs will grow rapidly in the coming years, just to replace the oil, fossil fuel-based uses with decarbonized energy, if we want to replace this, we're gonna need, Norway is gonna need significant new source of decarbonized energy in the production. So my understanding is that electricity needs are mostly covered by hydroelectricity, but hydro is indeed one of the most suitable and economical energy. But I understand that even if Norway still has room for additional hydro production, one question is if hydro can meet the growth in national demand. That's the first question. The second question is if hydro can serve the isolated regions of the country that's also have an increasing need for electricity. For example, I understand that in some localities in the north east of the country, up to 90% of the electricity can be imported from the neighborhood countries. So this dependence highlights the energy vulnerability and can also impact the economic competitiveness of these areas for industries. And these industries may choose to develop elsewhere than where they wanted to develop initially. So another question, I guess, is if Norway wants to continue exporting electricity at a competitive price. So if I'm correct, today around 15% of the electricity production is exported. So overall, I understand that there is three main challenges. First one is Norway to continue selling the excess of electricity at a competitive rate. The second point is to increase the production capacity to meet the rapidly growing electricity needs, just by compensating at least the carbonized energy used by industries and transport. And the third is to ensure the availability of electricity in isolated regions where the electricity demand exceeds the available supply and where hydro reaches somewhat its limit. So in my understanding, this makes it inevitable to explore alternative solutions for decentralized electricity production. And I think there are basically 2 or 3 options that are other than hydro for Norway, which is the wind, nuclear, or a combination of both. But I think we all know that these two energies provide very different quality of energy and also not at the same cost. In terms of, for example, cost per kilowatt hour, wind energy has to be subsidized to compete against hydro or electronuclear energy. And also in the industrial point of view, for the industrial activities, they need visibility, they need predictability, and also stability of the electricity supply. So when we want to make the choice between the wind and nuclear energy, that really plays a big role to know who is going to be the consumer. So the choice of technology is complex. Is even more complex because we have to consider all the point of views. So the technological point of view, of course, we just mentioned it, but also economical, social, environmental, financial, and also geopolitical point of view. As we know, Europe today is in an extremely tense situation regarding the energy supply, and the future, let's say, trajectories of each country will have a significant impact on the national, but also on the European energy security, and also on the price of the energy. So that being said, in Norway, it seems that concrete initiatives already underway on the adoption of nuclear energy in certain localities in Norway, and some municipalities seem already convinced, if I'm not wrong, in the interest of and are interested in the nuclear energy. So this is already, in my opinion, a significant step forward, because it means that debates, reflection, awareness about the reality of nuclear energy have already led to some changes. Also, about this awareness of the public, I believe it's important to demystify this nuclear energy. Take the time to understand the pros and cons, to make the most informed choices. And it starts by sharing as much as possible in this subject. And we need also to make it accessible to the large public, because nuclear is still perceived as a big and scary black box, kind of. So there is a lot of work on this. But as I showed you before, there is a phenomenal wealth of experience on this subject, around 100 million operating hours of nuclear power plants. So the information is available for who want to really have an understanding of the risk and the benefit of the nuclear energy. But also, even though we have all this information, and for example, in France, despite the economical benefits that nuclear energy brought to the country since the 60s, the 70s, there is no 1 week that goes without like negative articles about nuclear power in France, whether it's about radioactive waste, the cost of nuclear power, the incidents, and so on. So I think once again, it's important to, when discussing this topic, to really quantify the risk and the benefit. But it's true that operation of nuclear energy carries risks, but in my mind, all industries carries risks. For example, if we compare to the airplane accidents, they have, of course, they have to. We have to avoid as much as possible the airplane accident and crashes, but we know that there is the zero risk does not exist, and the risk of a plane accident, even though it's 1 in millions flights, and it's still too much, and hopefully it will decrease over time. I believe that it's a risk that has been accepted by travelers. So yeah, again, risks are present in every industries, but we have to be reasonable kind of in the assessment of the danger that it carries. Yes, about the dangers and accidents, I'm gonna talk here about Fukushima, that you all heard of. So there are risks in these industries. There are risks that are known and that are not acceptable to ignore. For example, in the case of Fukushima, the risk of an accident due to significant tsunami was known, but measures and investments had not been decided, especially on raising the protective dike here. Yeah, the dike in Fukushima Daiichi, for example, had a height of 5.7 meters, if I'm not wrong, and the dike in Onagawa, which is a bit north of Fukushima Daiichi, and a dike of 13.8 meters, and was not affected by the tsunami, even though it was even closer from the center of the earthquake. So I can understand that there might be an ideological aversion to nuclear power due to its complex and potentially dangerous nature, along with past disasters, even though technological advancements have improved the reactor safety. And also it's true that Fukushima caused significant material damage, but fortunately, it didn't cost any human lives due to the nuclear accident. So in order to improve all levels of safety, it's crucial that the governments and the nuclear authorities set up really strong requirements about nuclear safety before going ahead with a project. You can see on the right that after Fukushima, all the accidents are taken into account in the design of the nuclear power plants. So, for example, for the EPR, we reinforced here in the design the anti-seismic system. Also, we set up nuclear action forces, which are teams trained to come to the sites that face accidents. And also here, I show the backup diesel. So that was for Fukushima the main cause of the complications, because the diesel was located underground. So when the tsunami arrived, they completely drowned, and that way they lost the control room and many control of different valves of the plant. Also, one important point is this transparency and nuclear safety law that was adopted in France in 2006. And basically, the three main objectives was to put much stricter requirements for nuclear safety, and also to set up the independent nuclear safety authority, and to promote the even more the public information, consultation, debate, also on the risks. So yeah, I can understand that there is more comfort in renewable energy sources like hydro or wind or solar, which are perceived safer. But we have to remember that nuclear power actually generates less CO2 than these technologies, and also causes fewer deaths when considering the amount of energy produced. So that's, I think, something we have to keep in mind. Here, I'd like to take a step back a little bit to get an overview of the nuclear powered worldwide before we dive in even deeper in the different EPR projects. So around 440 reactors were operational in 2022 across 32 countries, and 58 additional reactors are under construction. Here, the nuclear energy accounts for about 10% of the global electricity, with the fossil fuels having the largest share. The first country, nuclearized country remains the United States, but China, I think United States have around 90 operating reactors today, but China is on track to take the lead in the coming years. And although China started the nuclear construction around the year 2000, they already have over 50 plants, and around 20 more are currently under construction. Here in the bottom right graph, we see that the construction of a nuclear power plant rapidly increased from the 50s to the early 2000s, and this growth was mainly motivated by the need of an alternative to fossil fuels, because nuclear could meet a rapid growing demand for electricity, mainly during this economic boom and fast industrialization. In the 70s. So I believe this is interesting. This is an interesting point here, because it gives us a sense of déjà vu, where the question was an alternative to fossil fuels. And today we have kind of the same question: what's the alternative to fossil fuel? And if we remember, back in the 70s, it was already clear that nuclear power was a key solution, despite all the risks, uncertainties, and the safety level that is not comparable to today. So the level of knowledge, expertise, or experience was negligible back then compared to today. But the choice of nuclear was massively adopted given the benefits of the energy. So however, after the 2000, the construction slowed, mainly due to the concern of safety. We had Chernobyl in the 90s and Fukushima in 2011. So many countries turned away from nuclear energy at that time. But today, Norway faces maybe an energy challenge, but I mean, maybe regarding the choice of nuclear, but there is this wealth of information and experience that I think is very valuable for making a reasonable decision, even though there are always risks and uncertainties. But this remains a reality for any industrial project, I guess. So here is a general overview of the EPR project. They were launched in 4 countries so far. So Finland, France, China, and England. The different colors represent the main stages of the project, starting from the signature of the contract, the start of the preparatory work, the civil engineering, the introduction of the reactor vessel in the building, the connection to the grid, and finally the commercial commissioning. So for France, the construction of the first EPR really marked the revival of an industry that have been dormant for 3 decades. We didn't build any nuclear power plants since the 80s. So that has been a big challenge to relaunch the industry and and that also impacted the delays and cost of this nuclear power plant in France. So looking back, we understand that complications, delays were inevitable for the first of a kind project. But this experience highlights the importance of recognizing the initial challenges associated with such an big and new industrial journey, kind of. So I think it's what is the most noteworthy is that there has been, despite all the delays, no compromise on the safety level that the power plant must achieve. And the safety authorities have done, I think, a really serious job in each country and demanded the suppliers to establish robust safety requirements that address all the identified risks that the safety authorities was managing, kind of. So for the EPR, each country, China, France, Finland, and England, imposed the specific requirements on top of the standard ones, which the supplier had to consider and integrate in the plant's design. So comparing the different projects to each other here, we can see that the projects that started last, China and UK, have actually reduced the construction time, especially considering that they were constructing 2 EPRs, while France and Finland have only one each. So this shows that the experiences gained from the initial projects have really benefited to the subsequent ones. Here, I'd like to focus on the, just a second, running out of battery. I'd like to focus on the EPR in France, but before presenting the table and the image in this slide, I want to provide you a little bit the context of the EPR project. So in the 90s, as I said, there was the Chernobyl disaster, and the French authorities wanted to build a safer nuclear power plant, and the EPR offered safety guarantees not present in conventional plants. So the EPR was designed to be more robust from the start, with increased redundancy in the backup system, as I showed you with the additional cooling independent systems. And the primary goal was really to reduce the risk of severe accidents or major incidents occurring in the plant. So also the EPR was at that time in line with the trend of more powerful reactors to generate energy. EPR is around 1,700 megawatt, where the conventional one are more around the 1,000 to 1,200 megawatt. So the choice of this size actually helped offset the manufacturing cost, because the construction cost is the most significant cost of a nuclear power plant. But the idea is that once operational, the plant can produce more electricity and reduce the fixed cost per unit of generated energy. So in the long run, this could really offset the higher initial construction costs. So the construction of the EPR began in 2007, and delays were quickly noted. EDF, as I said, didn't build a reactor for 25 years, and it required to renew the whole set of skills. So basically, learning was happening simultaneously with the construction, causing significant delays. And also in 2001, the landscape of nuclear energy changed because of Fukushima. So the French Safety Authority became even more strict in this inspection, which led to additional work and further delays to implement all the changes on the nuclear power plant. The construction was supposed to be completed by 2012. The initial budget was 3.3 billion euros, and the final cost soared to over 12.7 billion euros. So while some expected a slight delay at the beginning, I think no one anticipated almost 16 to 7 years of construction and the cost increase by threefold, which made it a very negative outcome for this project. So let's go back to the table here. So in December, the construction process started, and by April 2008, the construction had to be suspended due to cracks found in the concrete block of the nuclear island. So it took 1 year delay, and it cost 20% more of the initial budget. Then moving to December 2008, we had new problems in the concrete close to the reactor floor. Then 2010, we discovered issues in the metal structure and the concrete base, and the concrete. It was basically full of holes in the concrete. So from 3.3 billion, we then reached 5 billion euros. And additional delays for the project. So then March 2015, there was issues in the composition of the steel used for the reactor vessel and the cover and on the bottom. And the safety authority considered that the reactor vessel was defective, and that the excess of carbon in the reactor made it really unsafe. So EDF EDF, which is the constructor, conducted several tests and luckily successfully defended its argument in front of the safety authority. But several months have passed, so yeah, it was additional delays. Yeah, at the end, the safety authority judged that the margins, although reduced compared to what was initially planned, remained sufficient, and therefore the vessel could be kept in the current state, so they could move forwards. And then in June 2015, we faced faulty with the valves, safety valves in the EPR. And 2018, we identified quality gaps in welds of the main circuits in the circuit connecting the steam generator to the turbine that generate the electricity. So a bit to illustrate this weld problem, I put this image. Sorry, it's in French, but I think you will understand the different drawings. So in 2018, issues with welds were identified by the safety authority, and 8 significant welds were identified as needed to be repaired, which would lead to new substantial delays in the project. So on one hand, EDF said that the safety standards are sufficient to start the reactor, and that the welds can be repaired during the first 10-year shutdown. Also, there is this big shutdown phases every 10 years to inspect the nuclear power plant. So on one hand, EDF says that they can postpone, and in the other hand, the authority said that they have to repair it before the startup of the nuclear power plant. So yeah, just to show you a little bit here, the scenario or the solution proposed was to use robots remotely operated and designed for precision operations inside the pipe. So there is the robots coming here and work on the welds. Yeah, so EDF proposed to repair at the end to repair the welds around this year, just after the final commissioning of the reactor, and there is still discussions about this topic as of today. So that gives a little bit a taste of complications that happened, but we can hope that when the EPR is operational and operates for 60, 70 years, and hopefully new EPRs are gonna be built around the world, the high cost and the really long period of construction will be slightly forgiven, kind of. So we need to put on perspective the issues and the delays with the duration of the availability of the power plant in the long run. On this slide, you can see in the background the 2 power plant built at Taishan in China, which is not far from Hong Kong. If you recall the timelines that I presented in the previous slide, EDF started its project in France before the one in China. However, it's in China in 2019 that the first reactor was commissioned. So I personally joined the project during the final phases around 2016. And that was really impressive to witness the significant amount of manpower working on the plant in China. For example, EDF had between 1,000 to 3,000 people on site, where China could deploy 10,000 to 12, maybe 10 to 15,000 people on site for the construction. So yeah, that was an experience. I was working in this building here with the engineering teams. So in China, I was responsible for the backup systems, the one similar to what was lost in Fukushima, and also responsible for the emergency systems that would be used in case of a nuclear accident, such as, for example, the reactor meltdown, where the corium is released in the bottom of the container in the building. I was responsible for the commissioning of this system. But it's also important to keep in mind that the probability of such accidents is extremely low. But given the lessons from the past accidents and the assessment of all potential incidents, it's mandatory to have means to control this situation. So overall, the majority of the plant system are designed to ensure the plant safety rather than directly generate energy, as I said before. I would like now to show you a short video of the Taishan project. I will try to launch the video here. I hope you can hear it. Yeah.
JVC, a third-generation nuclear power unit of a joint venture between China and France in China's Guangdong province, has been unveiled for commercial use. The unit at Taishan Nuclear Power Plant is the first in the world to adopt the European Pressurized Reactor, a third-generation nuclear power solution supplied by French conglomerate Framatome. The double-wall containments designed for Taishan EPR units can protect reactors from catastrophes, including earthquakes and a direct strike from an airplane.
What you see now is the largest steam turbine generator unit in the world. Unit 1 at Taishan Nuclear Power Plant is also the most powerful single unit in the world, with a capacity of 1,750 megawatts. Every year, it could cut standard coal consumption by over 4 million tons and cut greenhouse gas emissions by over 10 million tons, which equals to afforestation of nearly 30,000 standard football pitches.
Taishan plant was built by TNP JVC, a joint venture founded by China General Nuclear Power Corporation, French energy supplier Électricité de France, and Guangdong Yudin Group. Its construction started in 2009, 4 years later than Unit 3 at Olkiluoto Nuclear Power Plant in Finland, and 2 years later than Unit 3 at Flamanville in France. However, The Chinese plant was the first among the 3 firms to initiate commercial operations.
对欧洲人来说，他特别大，他之前没干过，第一次干，所以他们在这个过程中，他们遇到的一些困难，他没干过这个，包括他们在民用方面，类似这种火力去交这么大的工程，他也没干过。我们国内私营企业啊，不仅是有这30多年核电的建设经验，那么有好多这个核电的工程这些大工程在国际上。随便我们拿出一个项目来说，都是一个非常了不起的。
Engineers were confronted with an array of challenges while constructing the Taishan project. Still, they ultimately managed to overcome all obstacles and complete the project.
当我们的进度持平的时候，心里面有喜悦，说，终于换了地位，我可以告诉你哪些地方你需要小心哦。那么你以前对我所有的开诚布公的这些信息啊，是有价值的，因为我也会把我的这个东西给你。
Many believe that the Taishan plant is a testament to China's nuclear power development capabilities.
这个合作的关系变化很大。刚开始我们是小学生，在台湾的时候，0117我们自己管理做主人啊，外方只是做一个顾问啊。到了台山这里，我们是完全自主管理，而且很疏忽我们的管理理念。所以就是从学生到主人，有可以跟外方进行这个比较优势的一个层面。
Experts predict that the Taishan project could offer valuable solutions for the construction of similar reactors worldwide, and it will play a demonstrative and supportive role in the joint construction of the Hinkley Point C project in the UK by CGN and EDF.
你看英国它是 HPC 建EPR 项目，它需要我们合作啊。那么将来是不是我们比方说在合作建其他的这种堆型也好，都有这种可能？因为这种可能呢，就是说双方合作强强联合以后呢，就是说这个有利于这个提高生产力啊，在提高这个安全性的情况下，都有利于降低成
本。Yeah, so the construction of Taishan EPR projects is estimated about 6 billion euros per reactor and approximately 12.3 billion for the 2 EPR reactors in Taishan. And for comparison, the construction of the Finnish EPR in Olkiluoto was estimated around 8.9 billion euros. And as I said, France now is reaching slowly but surely 12.3 billion euros. So the delays in the EPR project in Taishan were due to a series of factors, including the technical issues, especially defects on the design of the reactor vessel welds. Once again, the welds were really challenging in all the EPR projects for the EPR. So the weld showed geometry defects that could compromise the strength and increase the risk of rupture. So these defects were attributed to mistakes during the welding procedure design, and in the same time, chemical composition defects in the metals were identified in the welds, potentially reducing the strength and also increasing the risk of corrosion. But despite all these challenges, the Taishan EPR project successfully passed several milestones, And it also provided learning opportunities and strengthened also the international relationships relations in the nuclear field. So yeah, first working on a nuclear project between two countries as a lesson learned really involves cultural differences and different standards and regulations. Yeah, here, and this can lead to challenges in the communication, the coordination, and also the mutual understanding of business and technical practices. Also, France and China had to really closely collaborate to transfer the knowledge and technical expertise, and transferring the skills needed for the construction operation of such a large nuclear power plant was really challenging. So Chinese, for example, when I worked in the Paris office, Chinese came to France for several years to start the knowledge transfer and prepare the Chinese team to build the reactor in China. Also, second, another important point is that the second, so that's unit 1 here, that's unit 2, and this second unit was built by the Chinese alone, but in parallel, means that there was no specific support from the French teams to build the second one. And basically, yeah, the second reactor started 1 year after the first one, and yeah, they were really close during the construction phase. Were really close for both during the construction of both reactor. Yeah, another point, as is often the case in projects of this magnitude, the delays and cost overruns can happen, and coordinating different teams, meeting deadlines, managing technical enforcing circumstances can be complex and impact the project initial schedule and budget. So the right choice of team members, also the management and their level of expertise is really crucial in this big project. Another point here is harmonizing the safety and regulatory standards between the two countries can be really a challenge, and ensuring that the power plant meets the requirements of both parties, the client and the supplier, while guaranteeing the highest level of safety and compliance with the national regulation is really a challenge. And these regulatory requirements has been, the challenge behind it has really been noticed in all the EPR projects. And here, last but not least, the cultural and language difference really can create a big barrier in communication and collaboration. And even though we were a mix of French, Chinese, and also Germans in same open space to work, the communication, but also the approach to face technical issues were really not easy. So this is my sense lesson learned to really keep in mind during like international cooperation for such big projects. So I'd like to show you here in this slide the progress of the EPR project in UK. So you will visualize the progress of the construction in I think it's September 2023, so 6 months now, 5 months ago. But first, before playing the video, I'd like to present you a bit the financial deal between EDF and England regarding this EPR construction. So it's a lease and power purchase agreement. So EDF commits to build and operate 2 new EPR in the south here in the south west of England, which is called Hinkley Point. And in return, England will guarantee EDF a fixed price for the electricity produced by the EPR for a period of 35 years. So the financial deal between EDF and England is really a challenge for both parts. EDF on one side hope that the EPR will be a commercial success and will strengthen its position in the nuclear energy market. And in the other side, England aims to diversify its energy source, reduce also the dependence on fossil fuels through the EPRs, and also have to pay back EDF through the tariffs. So I will play the video. I hope it's gonna work.
Welcome to Hinkley Point C, where we're building Britain's first nuclear power station in more than 30 years. Night and day, it'll power 6 million homes and will be crucial in helping us achieve net zero and stronger energy security. Right now, we're busy working towards a really big milestone in the project's construction. Let's go and find out more. Welcome to the heart of the first reactor building. The teams are getting ready to lift the 245-ton steel dome on top of the building. It will be a spectacular sight and a significant milestone for the project. Below me, we have installed the support ring, which will hold the reactor in place. The reactor arrived on site early this year and will be installed next year. You can see we poured the concrete around the big prefabricated pool, which will be home to the reactor for its operational life. Next, we'll fit the huge equipment hatch, which will be installed on this opening behind me. It will open and close, allowing our equipment to be moved into the reactor building during construction and operation. In the coming months, we'll put the polar crane on the brackets, which are being prepared above me. It's a huge rotating crane that will sit under the dome. It's under construction here on site and will be lifted in one giant piece. All these elements have to be completed before we can lift the dome, which is just over there. Good morning. We're here at the dome, where we're making the final preparations before the dome will be lifted into place later this year. Let's go and take a look. Wow, look around. We're now under the dome itself. We've spent a lot of time working on the steel structure, carrying out the manufacturing, welding, coating, and services installation and testing. And in just a few months, it'll be lifted on top of Unit 1 by Big Carl, the world's largest land-based crane. There's a real sense of anticipation and excitement, and we've been building for this moment since the project began. Once the dome is lifted, the first reactor building will be weatherproof, so mechanical and electrical teams can really get to work on installing the pipes, the equipment, and the cables. We'll also start introducing the big nuclear components like our steam generators, which have finished initial testing at Framatome in France. Now, all these components need to be controlled from one central point. And that central point is our main control room, and it will be installed right here on this concrete slab. We're busily finishing the walls that will sit around the main control room, but it won't be long before it'll look just like this. Our trainee reactor operators are already using the simulator, which is an exact replica of what the control room will eventually look like. The actual control room is on the other side of the site and will be lifted to where I'm standing before Christmas and then fitted out. It will control the reactor building and also the power generation in the turbine hall. Unit 1's turbine hall is really taking shape. Right here, we'll install the world's largest steam turbine, the Arabelle, made by our colleagues at General Electric. The turbine will generate electricity using steam generated from the heat in the reactors. These huge white structures above my head are the roof trusses, taking the hall to its full 50-meter height. We're now gearing up to install the 300-ton crane. It's under construction in Avonmouth and will be used to install and maintain the equipment in the turbine hall. So that's above ground. Now let's go underground. I'm now on my way out to the end of the tunnel, which will return water to the Bristol Channel, more than a mile out to sea. It's big enough to take a train and is one of 3 tunnels which will circulate our cooling water. I'm right at the end of the outfall tunnel, where 23 meters above us, 2 huge jacket vessels are drilling down through the seabed. This summer, they installed 6 giant steel casings to form shafts. We'll join it with the tunnels down here, and we'll dig out to make the connection. It's some of the most complex work in our entire project. Back here on shore, the pump house is progressing really well. Civil works are now 2/3 complete, and the mechanical and electrical works are underway. Now let's go and check out one of my favorite views of the site. From here, you have a great view of Unit 2, our second reactor. After slowing down during the pandemic, work is progressing well here, particularly on the concrete inner and outer containment structures on the reactor building. And it means we'll be ready to install the second steel inner ring later this year. Construction of the whole of Unit 2 and its systems is really benefiting from the lessons learned over at Unit 1. Many tasks are achieved in 20 to 30% less time than on Unit 1. That replication principle underpins our plans to build an identical power station at Sizewell in Suffolk. And that's it for our latest tour. I am so proud of the people working here on site and the thousands of people working on this project right across the world. Next time you're here, the dome will be on Unit 1 and the site will have transformed again. More of our mechanical and electrical work will be underway, and we'll be installing and testing more equipment so that it's ready when the power station becomes operational. See you then. Thank you.
So, as you can see, it's a lot of concrete and steel, and the dome is also now installed on top of the containment structure, which will welcome the core reactor. So that concludes the virtual tour of the EPR. And now I'd like to present you the competencies, the skills that are required, let's say, for the construction and the operation and maintenance of nuclear power plants. So in terms of skills, I would say even though Norway has not commercially operated its nuclear power plants, it has, I believe, really a solid base, a solid knowledge already on the nuclear or electronuclear field. And it's essential to note that nuclear physics, the skills of nuclear physics represent only a small percentage of the skills required for the construction of the nuclear power plant. So there is a website in France. Just give me a second now. Trying to. I don't have the pen anymore. So there is a French website for nuclear energy industries that provide a list of companies supporting the development of the nuclear industry in France. So it goes from construction, electricity, mechanics, pipe, valves, ventilation, chemistry, IT, of course, and the boxes presented on the slide show all the competencies offered by this association or group of industries that support this sector in France. Also, yeah, we have to think it's important to say that for France, after the government announced 2 years ago the massive investment plan of 50 billion euros to relaunch the nuclear electronuclear sector, but also to launch the more renewable energy. So along with this announcement, this association of industries submitted a skills action plan to the ministers in April last year. So the action plan aims to secure the skills required by the nuclear sector over the next, let's say, 10 years, given the significant challenge in terms of human resources, but also in terms of industries that will support all the projects. So what I understand in Norway, what I believe is that oil companies already have the necessary, in my sense, the competencies for developing large part, at least a large part of the nuclear construction. As you could see, it's a lot of concrete and steel and valves and ventilation, but this is nothing closely related to nuclear itself. And so by understanding, I guess, the value chains, the existing value chains in the oil industry, I think it's possible to transfer this knowledge and find the synergies between the oil and the nuclear industries. Also, another point is compared to the beginning of the oil era in Norway, back in like a few decades ago, the country has now much more expertise in the nuclear field, thanks to your experimental reactors, for example. But also you have neighboring countries, Sweden and Finland, that already developed expertise in this area. And I understood that Nordic energy collaboration or collaboration in general is pretty successful. So that's an additional point that makes it maybe easier to build the knowledge about this industry. So now I would like to switch a little bit and jump to small modular reactor, because the EPR could be of interest to Norway. However, for Norway, which already has a robust, let's say, energy mix with a significant share of hydroelectricity and even more room for hydro, maybe a project of this magnitude might not be the most let's say, flexible or suitable solution. So in contrast, the small modular reactors maybe could suit a bit better Norway, because they are smaller, they are modular, they also offer they basically offer sufficient production capacity to meet really specific needs. The SMRs, for example, are designed to be more to be more flexible, but also are faster for the installation, and they can adapt to different energy needs, including for isolated regions, for example, or small scale uses, like, for example, for industrial facilities. So what's happening today in the nuclear industry is that the nuclear industry is now going toward smaller power with more safety, less waste, more flexibility, and also requiring less capital. So far, we have been constructing big and very powerful reactors like the EPR, because the bigger the power plant, the cheaper the cost of electricity. So what's happening now is that we are in a really major shift and a change in the logic, where these big conventional reactors are really being questioned. So this slide shows on the bottom left, I can have my laser back here, yeah. The breakdown of a large reactor. So you can see that around 60% of the cost is due to the reactor construction alone, and around 25% for operations and maintenance, and only 10% for the fuel. Yeah, for the fuel cycle. Also, the construction duration for this type of nuclear power plant is around 10 years. So to face this high construction cost, there has been this shift toward constructing this smaller power station. So these lower power reactors are more cost effective. The construction phase is shorter. It requires also, as I said, less capital. It's easier to operate, to maintain, to decommission as well. And because the size is smaller, it's also more simple to manage the safety systems. The design of the safety systems is also make it simple to operate. So yeah, SMRs aims to be more versatile. And here it's a bit too small, but the SMR will produce electricity, but also aim to produce heat and help to produce hydrogen as well. So it's more flexible than the conventional reactors. So where the conventional reactors are about 1,000 to 1,500 megawatts, these small reactors will be up to 300 megawatts. Yeah. Here you can see that the construction process will be carried out in modules. within dedicated facilities, and we'll also have the possibility to build multiple reactors on site. So there is a strong emphasis on standardizing and building series of these power plants in a row to make it basically the idea is to decrease the price by reaching the scale of production. So it's going to be, the idea is to have like a mass production of SMRs to really reduce the price. Yeah. Also here, just want to show you that there is two type of reactors, generation 3 and generation 4. Generation 3 is basically the EPR generation, and the fourth generation said is not yet mature, but it's going to be more efficient in using the nuclear fuel. Will produce also less waste, more safety, but we will have to wait probably, I don't know, 10 to 20 years maybe. So this generation 3 SMR should be ready by 2030. I mean, that's the estimation, but then we'll see if it really happens. Yeah, final slide here, just to show you that today actually the most nuclearized countries are interested in nuclear reactors, but they are primarily interested in exporting and selling the technology, not necessarily for domestic installation. For example, France here has this project, but they will focus mainly on the EPR for the national territory and the small SMR for exports. I think England is not here, but we'll use part of the new SMR in England, but it's also made for export. So currently, I think we have roughly 70 different projects of SMRs. So it means that there is a lot of competition, but it looks like there is the market for it. The OECD, for example, estimated that around the world, around 20 gigas of electricity capacity will be needed. So, for example, if we think of SMR of 50 megawatt, it represents already for 400 reactors, and that's the market for the next 20 years. Yes, that's it. I hope, I mean, I was very long, but I hope you had valuable information, and I'm open to questions if you have any. Thank you.